Today we will discuss about AC through a capacitor. So when an alternating voltage is applied to the plates of a capacitor, they are first charged in one direction and then in opposite direction. Here I have shown in figure a capacitor is connected to an AC supply. So when it is connected to an AC supply, it's charged to and fro direction, or it's charged in one direction and then in opposite direction. So the result of to and fro motion of the electrons around the circuit is that an alternating current flows through the capacitor and the connecting wires. So because of this to and fro charging, energy is flowing through this capacitor and the connecting wires. When the voltage across the plates of the capacitor has reached its maximum value in one direction, the capacitor is fully charged. No charge flows in, so that the current has reached its zero value. So when the voltage applied across the plates of the capacitor is reaching its maximum value in one direction, then the capacitor gets fully charged, and after this no charge flows in, so that the current will reach its zero value. That means fully maximum value or maximum charge value means the value is steady value, so there is no change in charge at this point, so that the current will be zero, because current is the rate of change of charge dq by dt. Let C be the capacity of the capacitor and an alternating EMF is equal to E0 sine omega t, and if Q be the charge acquired by the capacitor at any instant, then the potential difference, which is represented by V, between the plates at this instant is given by V is equal to Q by C, which is equal to E0 sine omega t. So we are applying a voltage E, a potential E, which is given by E0 sine omega t, which is a sinusoidally varying AC current or AC supply. And let this voltage causes a charge Q on the capacitor across the plates. The potential difference V across the capacitor developed can be represented as V is equal to Q by C, which is equivalent to the applied voltage. So we can write V is equal to Q by C is equal to E0 sine omega t. From this, Q is equal to C E0 sine omega t. Then the current through the capacitor at that instant is given by I, which is equal to dq by dt. This is equal to, this can be obtained by differentiating this equation. So differentiating sign, we will get cos omega into omega. So we will get I as omega C E0 cos omega t. So we can write this expression as E0 by 1 by omega c. This is same. And cos omega t as sin omega t plus pi by 2, which will give you I is equal to I0 sin omega t, where I0 is E0 by 1 by omega c. The maximum value of the current is then given at t is equal to 0. At t is equal to 0, this value of sine function will give you maximum value, that will give you the maximum value of current. So we know E is equal to E0 sin omega t, but we got I is equal to I0 sin omega t plus pi by 2. So from these two equations, it is clear that the current leads the applied EMF by a phase of pi by 2. Okay. the vector diagram of this is shown here. Here, if this represents the voltage, then the current is represented in this direction, that is a leading of voltage by 90 degree. And if this is voltage, this is the direction of current, leading of current by the current of the voltage by 90 degree. The term 1 by omega c corresponds to the resistance of the capacitor and is called the capacitive reactance. That is, from this equation here, I is equal to E0 by 1 by omega c. So naturally this will be, the term corresponds to resistance. Since in this circuit we are supplying AC, the resistance corresponds to capacitive reactance. So 1 by omega c can be written as 1 by 2 pi f c, since omega is 2 pi f, and is given in ohms if c is in farads, which are the standard units of this. It is commonly denoted by Xc. So the capacitive reactance is denoted by X suffix C. In an inductive reactance, the applied EMF is 90 degree ahead of the current, while in capacitor reactance it is 90 degree behind the current. They will this be represented in opposite directions in a vector diagram. So we have seen in our previous class about the inductive reactance and circuit containing inductor and resistance. So from those we have seen that the applied EMF ahead of the current or leads the current by 90 degree, but in a capacitive reactance it is 90 degree behind the current. So in a vector diagram, these two are represented in opposite direction. Xc, which is 1 by 2 pi fc, shows that the reactance of a capacitor is inversely proportional to the frequency of the alternating current. It is clear from this equation. F is in the denominator, so it is inversely proportional to the frequency of the alternating current. If the frequency of an AC passing through the given capacitors is high, then 1 by 2 is high, 1 by 2 pi fc, or capacitivity reactance will be small. And we can say vice versa. If it is small, the capacitive reactance will be high. So if the frequency is high, the capacitive reactance will be small. Then the capacitor is an AC path for very high frequency currents. Such a capacitor is called bypass capacitor. In the case of high frequency current passing through the capacitor, the capacitive reactance is very small. That means the capacitor is an AC path for this high frequency current. Such a capacitor is called bypass capacitor. And if F is small, 2 pi Fc is large. Since F is in denominator and 2 pi Fc is large, that means capacitive reactance is large. That means it offers a great resistance to the passage of the low frequency current. And if F is equal to 0, and 2 pi Fc means leads to an infinite value, then the capacitor will act as a complete stop for DC. So F is equal to 0 means the frequency of the applied EMF is 0. That means the applied EMF is purely DC. So then the capacitor will act as a complete stop for DC, means it blocks DC current and is then called a blocking capacitor. An AC may thus be controlled by using a capacitor in its path. Okay, so the reactance of a capacitance of 2 microfarad at its 50 cycle per second is 1 592 ohms, while at 5000 cycles per second it is 15.1. This is just an example. So from the above discussion, it is clear that a capacitor is very often used to separate AC from DC. Suppose that a battery and an audio frequency which is having frequency 7000 cycle per second, alternating voltage are in series with a circuit contain headphones of reactance 150 ohms and a capacitor of 1 microfarad capacity. Then what happens? DC is eliminated by the capacitor since it offers infinite resistance to DC, but the AC will pass through the capacitor and the phone. This is quite clear from the above discussion using the capacitive reactance formula 1 by 2 pi Fc. Okay, so this is about the AC through a capacitor component. Now we will discuss about AC through the combination of capacitor and resistor. That is, this is a CR circuit. So we have already discussed the AC through the resistor and we have discussed now the AC through capacitor. Now we will discuss AC through the combination of this capacitor and resistor. So I have shown here a resistance which is connected in series with the capacitor and an AC is applied. So let E be the applied EMF, IQ be the charge on the capacitors at any instant, R be the ohmic resistance of this, which are usual notations we used in such circuits. And now the total EMF in the circuit can be written as the EMF or the potential dropped across this component and this component. So the applied EMF E can be written as the drop across resistance R, which is IR, plus that across capacitor, which is Q by C. Let I is equal to I0 sin omega t be the current in the circuit. So that I is equal to dq by dt. Means I can be represented as the rate of change of charge. So this is dq by dt, which is nothing but I0 sin omega t. So we are supplying current of I is equal to I0 sin omega t. Okay. Then the Q can be evaluated from this expression by integrating this value. So Q is integral I0 sin omega t. Here one dt. Here sin omega t dt, which will give you a value minus I0 by omega cos omega. So integrating this will give you minus cos omega by omega. So applying this value of Q in this expression and the value of current applying the value of current and Q in this expression, I is equal to I0 sin omega t and Q is we got from this expression. So E will become I0 R sin omega t minus I0 by omega c cos omega t. And we are doing here is we are taking I0 outside the bracket as common factor and will remain with R sin omega t minus 1 by omega c cos omega t. And now we will multiply and divide the equation throughout by square root of R square plus 1 by omega square c square, just as we have done in our previous cases. So we will end up with this equation just multiplying and dividing, so that nothing will happen to this equation. And what we are doing in the next step is we are putting sin phi as 1 by omega c into square root of R square plus 1 omega square c square, and cos phi as this, that is substituting for this term and this term. And then this equation will be of the form sin omega t minus phi. So we are ending up with an equation. So this term will remain here, this term and this term and this term together will give you sin omega t minus phi. So we will get an expression for EMF as E is equal to I0 into square root of R square plus 1 by omega square C square sin omega t minus phi. From above equation, tan phi is equal to 1 by omega c by r. So from these two, we will get the phase phi as 1 by omega c by r. Okay. Thus it is seen that EMF lags behind the current by I. So here we have seen from this equation I is equal to this factor and sin omega t minus phi. But our current equation was I0 sin omega t. So from this, comparing these two equations, it is clear that the EMF is lag behind the current by a factor of phi. Where phi is given by tan inverse 1 by omega CR. Okay. When omega t minus phi is equal to pi by 2, we get the maximum value of E and current from the above equation. So the sine function will have maximum value when it's when this angle will become pi by 2. So that means omega t minus phi is equal to pi by 2. Okay. Now I0 is equal to E0 by square root of R square plus 1 by omega square C square. This is clear from this expression. So when this angle is pi by 2, this will give you maximum value of E0. That is when it will give you E0 is equal to I0 into square root of R square plus 1 by omega square C square when omega t minus phi is equal to pi by 2. This is the maximum value of voltage. From this I0 will get E0 by R square plus square root of 1 by omega square C square, where this term represents the impedance of this circuit. Using RMS values, we have I is equal to E by square root of R square plus 1 by omega square C square. Here 1 by square root of omega square C square is nothing but the capacitive reactance, which is Xc. Okay. If R is equal to 0, then I will be purely E by Xc. Here Xc is 1 by omega c, so that I is equal to E into omega into c. So that means 2 pi f e c. This shows that the potential difference across the terminals of a capacitor carrying given AC varies inversely as C and F. Inversely as potential difference across the terminals of a capacitor carrying a given AC varies inversely as C and F. This is clear from this equation. So this circuit, that is a combination of CR circuit which carrying an AC current, will have many applications. Some of these are quoted here. That is, a practical application of this circuit is to be found in the coupling between two stages of an RC coupled amplifier. It also contributes a low pass filter if the output is taken from across the capacitor. The combination of low pass and high pass filter of this type is used for tone control in radio receivers. Here cos phi, which is R by square root of R square plus 1 by omega square C square, is called the power factor of the circuit. So that's all about AC current passing through the combination of CR circuits, and we have discussed the AC through capacitor component also. So that's all for today.